Let's look at some of these differential equations as practice for our AP exam. This is a non-calculator question. It says at time t equals 0, a boiled potato is taken from a pot on a stove and left to cool in the kitchen. The internal temperature is 91 degrees Celsius at time t equals 0. Internal temperature of the potato is greater than 27 degrees for all times t greater than 0. Internal temperature can be modeled by the function h, which is represented by this differential equation. dHdt equals -1/4, parentheses, h minus 27, where h is measured in degrees Celsius and h of 0 equals 91. So this tells us that at time t equals 0, the internal potato temperature is 91 degrees. Write an equation for the line tangent to the graph of h at t equals 0. Use this equation to approximate the internal temperature at time t equals 3. So in order for us to write an equation of the tangent line, we need to find order pair and we need to find slope. Well, order pair should be easy because we have that information already provided for us. H of 0 equals 91. So to find the slope, we have to be able to use some sort of a derivative formula, which we do have. That's what the dHdt is going to help us with. So dHdt, we're going to use this -1/4, parentheses, h minus 27. Now h represents the internal temperature, so we know that the internal temperature we're talking about is at time t equals 0, which is part of our order pair, which is that 91. So we're going to stick that 91, that temperature value, in for h, which will represent the exact temperature at this moment in time, which we're concerned about, t equals 0. So once that h gets replaced with 91, we can clean this expression up, and whatever the numeric value is going to represent the rate of change of the temperature at that moment in time. So h prime of 0 is equal to -16. Right? So now we have our order pair, we have our slope, and now we just plug it into our point slope form. Right? So y minus y sub 1, 91, is equal to m, which is -16, times x minus 0, or we can go ahead and use t to represent our independent variable. So y is equal to -16t plus 91. We can also think of y as our h approximation equation. Our temperature is equal to -16 times the value of the time in terms of seconds, time in terms of minutes, sorry, plus 91. So we have our equation, but it's asking for the approximation. So here is our linear equation that we're going to use to approximate. So we want to figure out what is the temperature at t equals 3. So using this line, we're going to approximate it. So plug 3 in for t, -16 times 3 plus 91. So approximately, according to this equation, the temperature at 3 minutes after the potato has been taken out is going to be at 43 degrees Celsius. Okay, for part B, use dth over dt2. This is basically using the second derivative function to determine whether our answer is an underestimate or an overestimate of the internal temperature of the potato at time t equals 3. So let's find the second derivative equation. Now, to find the second derivative equation, we're going to be working from that first derivative equation. We're going to work from that dHdt. So dHdt, we're going to find the second derivative. And to do that, we're going to have to find the derivative of each of these terms. So -1/4 is the coefficient that's going to stay. H is going to become h prime, which we're going to call dHdt. And the 27 is a constant, so that's going to go away as well. So our second derivative is just -1/4 dHdt. But to make it easier for us to evaluate, we're going to replace the dHdt back in terms of h. So we found the second derivative, which has dHdt in it. We're going to replace dHdt in terms of h. So dHdt can be replaced with -1/4, h minus 27. If I clean this up, then I have a version that's easier for us to interpret for the second derivative equation, which is 1/16 parentheses h minus 27. So we want to know whether at t equals 3, we want to know whether this temperature is going to be an overestimate, or whether our equation is going to be an overestimation or underestimation, right? Whether this approximation is over or under. So let's think about what happens with h, right? We know that up until t equals 3, the temperature is going to be starting at 91, and it's going to keep falling. But up until that third minute, it's going to be way above 27 degrees, right? And the reason why I'm pointing that out is because if we look at that h minus 27, we know that the temperature is always, at least in that first 3 minutes, it's always going to be above 27. And so we know that because it's above 27, this expression is always going to produce a positive value. And if this is a positive value, that means the second derivative function is always going to be positive, at least when my temperature is above 27 degrees. And if my second derivative value is positive, that means it's part of a concave upgraph. And if it's part of a concave upgraph, here's a visual, then any tangent line, any approximation, any line that is tangent to a portion of a graph that is concave up, we know that any point on this curve is going to sit nicely below the curve. So any point on this line is going to underestimate the actual value on the curve. So we can say, because the graph is concave up, we know part A, this 43 degrees, is going to be an underestimation of the actual temperature at t equals 3. For part C, we're going to be solving our differential equation. We're asked to solve for g of t given this derivative equation. So we have dg dt, and I'm going to go ahead and just cross multiply. Okay, so anytime I'm solving a differential equation, I like to cross multiply so I can get everything up in the numerator level, and then I can decide, okay, what can I move so that I can isolate and separate my different variables. The g in this case is going to represent my dependent variables, so I'm going to try to combine all the g terms on the left side. And then my independent variable is my t, so anything that is t or anything that is a coefficient that I can move to the right side, I'm going to go ahead and do that. So I think, so I see that what we can move over is this parentheses, right? This g minus 27 is stuck together. I need this g over on the left side, so we're going to divide it over to the denominator. But I'm going to leave the negative 1 on the right side. Just makes things cleaner if I can have my left side as minimal as possible. So once I divide this over, I know that I have to bring this up to get it ready for use substitution and power rule. And the right side, I just push the negative 1 out in front, and a 1 dt just indicates we're taking the antiderivative with respect to time. We let our u value on the left side be g minus 27. We find the derivative of u with respect to g, which is 1. G becomes 1. 27 goes to 0. Once we make our substitutions on the left side, we have integral of u to the negative 2/3 times du. That's a nice rule to follow with power rule. We do power rule, add 1 to the exponent divided by that new exponent. Negative 1 integral becomes negative 1t plus c. And now I can push that 1/3 up as 3, replace the u back in terms of the parentheses, and I'm going to go ahead and use this time to solve for c, because I would rather do it now than later when I have to deal with the cube and a little bit more messiness. But ultimately, you can solve for c anytime you want, either at the end or as soon as it appears. So in this case, I'm going to go ahead and solve for c as soon as it appears. I'll plug 0 in for t. That's my independent value. Plug 91 in for temperature, my g value. So 91 g gets replaced with 91. T gets replaced with 0. 91 minus 27 is going to be 64. Cube root of 64 is going to be 4. 3 times 4 is 12. 12 is my c value. So I go back to where I initially made the substitutions to solve for C. Replace the C with 12. And now, algebraically, I just want to solve for G. So divide both sides by 3. Cube both sides. So, and then I add 27 to both sides, and that will allow me to solve for G. But let's see here. I think it's asking for a little bit more. It's asking for find an expression for G of T, which we did. And then based on this model, what is the internal temperature at time T equals 3? So here's our G equation. Didn't have enough room below, so I brought it up to the top. I added 27 to both sides. So G of T is equal to negative T plus 12 quantity over 3 quantity cubed plus 27. Replace T with 3 and clean this up. I get 9 over 3, which is 3. 3 cubed is 27. 27 plus 27 is 54. So using this differential, or using this equation that we found by taking the antiderivative of our differential equation, we can say our temperature at T equals 3 is going to be 54 degrees Celsius.